Hello everyone, my name is Siki Fan, and my presentation is about Chow Liu algorithm and one of its improvements. Here are the three main reference papers about this presentation. Chow Liu algorithm was first introduced by Chow and Liu in 1968. It's an efficient method for constructing a second-order product approximation of a joint probability distribution. Let us think what we learned in class. We learned in class that how to design a system that generates expected data we want. But Chow Liu algorithm does another thing. It helps us learn the structure of the system when we're given the data. For example, when we're given a joint distribution like P of x1, x2 to x5, we can approximate it as a P prime, which equals to P of x1, P of x2 given x1, P of x3 given x1, and so on. It has a property that each new term in the product introduces just one new variables. And the Chow Liu algorithm can help us approximate the P prime, which has a minimal KL distance to the actual distribution P. But why we need the approximation for the joint distribution? There are two reasons. First, from the approximation, we can construct a first-order dependence tree. And from the tree, we can find the relationship and dependence of the variables. For example, for the joint distribution in the previous slide, which can be approximated as P of x1, P of x2 given x1, and so on, we can find the conditional independence of the variables, like x3 is independent of x1 given x2, x5 is independent of x2 given x4, and we can also construct a first-order dependence tree like that, which can help us approximate the relationship between different variables, like relationship of parents and children. And how we can calculate the approximation P prime? The Chow Liu algorithm tells us we can find a tree that has a maximum mutual information between pairwise variables. In fact, there are two steps. The first step is to compute the mutual information IXI XJ for each pairwise nodes xi and xj, and then find a spanning tree that maximizes the sum of mutual information IXI XJ, for which xi and xj are connected to each other in the tree structure. In details, we first compute the mutual information between each pairwise nodes IXY and XJ. Using its definition, IXY XJ is equals to the sum of the P of Xi XJ log P of Xi XJ divided by P of Xi P of XJ. And for finding a spanning tree that maximizes the sum of the pairwise mutual information, we first form a set of mutual information that I is equals to I12, I23, and so on. And this set has a descent sequence. According to the set of mutual information we computed before, now we can construct our spanning tree. First, consider the largest pairwise mutual information I12. We connect x1, x2 based on its largest pairwise mutual information. Then consider the second largest I23, and we also connect x2 and x3. The third largest pairwise mutual information is I13, but we already have a path from x1 to x3, which is x1 to x2 to x3. So we just ignore this one and jump to the fourth I24. We end the edge from x2 to x4. And so on and so far, we will finally get a spanning tree like following, which is what we wanted. After we find the spanning tree structure like this, we will get that the maximum of the sum of pairwise mutual information is the sum of mutual information between x1, x2, x2, x3, x2, x4, and x4, x5. And then we can get the conditional independence from the structure that x3 is independent of x1 given x2, x5 is independent of x2 given x4, just like what we learned in Markov chain. And then we can also get the approximation of the joint distribution and decompose the joint distribution as P of x2, P of x2 given x1, and so on and so forth. In this slide, I will make some derivation and prove the Chow-Liu algorithm, like what professor did in the class. First, consider the definition of the KL distance from P to P prime. It is equals to the minus of sum of Px log P prime of x divided by Px. We can separate this term into two terms. The first term will become the minus the sum of Px log P prime of x. The second term is the sum of the Px log Px. Because we have some dependence relationship in the structure, so we can change the P prime of x into the sum of P prime of xi given xji, which xji has some dependence relationship to the xi. And then we can use the relationship of conditional probability to the joint district probability. Then the that is P prime of xi given xji is equals to P prime of xji divided by P prime of xji. And we can add one term P prime of xi into the denominator of the first term. Then the first term will become the minus of the sum of Pxi log P prime of xi xji divided by Pxi P prime of xji. And the third term will be the minus sum of the px xi log P prime of xi. And the third term will stay the same, that is the sum of Px log Px. For the first term, we can change the Px in the first term into the sum of the P prime of xi xji based on sum of the xji. And the third term, we can change the sum of Px into the sum of the P prime of xi. It will be equal because it's just based on the variable itself. Then the first term, we can easily find that the P prime of xi xji xi log P prime of xi xji divided by P prime of xi P prime of xji is just the mutual information between different pairwise variables. So the first term will become the sum of the pairwise mutual information. The second term is we can also find that the P prime of xi log P prime of xi is just the entropy of the xi. So the second term is also becomes the sum of the entropy of the different variables. The third term is just the entropy of the whole variables. Then we will have the expression for the KL distance from the P to P prime, which is equals to the minus the sum of pairwise mutual information plus the sum of entropy on different variables minus the entropy on whole variables. But we can find that when we're given the data, the sum of the entropy on different variable and the entropy on whole variable will be fixed, which means that the KL distance from P to P prime is just related to the sum of the pairwise mutual information, and it has a negative relationship, which means that when we have a larger pairwise mutual information, we will have a smaller KL distance from P to P prime, and we will have a better approximation. And that is what Chow-Liu algorithm did. Chow-Liu algorithm is to find the maximum of the sum of pairwise mutual information. Thus, the Chow-Liu algorithm can indeed construct a second-order product approximation of a joint probability distribution. And that's the proof for the Chow-Liu algorithm. However, Chow-Liu algorithm have some problems and weaknesses. First, actual distribution may not be in fact a second-order dependence tree in real data. In fact, in many cases, the structure is very complex. Second, the Chow-Liu algorithm needs a large amount of data to ensure the accuracy of mutual information. If we do not have the huge amount of data, then we cannot calculate the pairwise mutual information correctly, which means that we cannot make a good approximation. Therefore, there are many other methods trying to improve the performance of Chow-Liu algorithm. And here I want to introduce the one new method, that is the minimax estimation, which is introduced by J. Jiao, K. Vakate, Y. Han, and T. Wiseman in 2050. What does the minimax estimation want to improve? Because as we know before, the Chow-Liu algorithm uses empirical mutual information to estimate true mutual information. This can perform very bad when deal with large alphabets, and the minimax estimation is trying to improve the performance when deal with the large alphabets. Here is a graph to describe how bad the performance will be when deal with large alphabets. We can see that the mean square error become very large when the number of variables become very large. So what does the minimax estimation do to have a better estimation? In the previous slides, we know that the Chow-Liu algorithm needs a huge amount of data to ensure the accuracy of mutual information. Therefore, the minimax estimation considered to change the formula of estimation entropy to have a better estimation when deal with large alphabets. Then we can have a better estimation of the mutual information, and then we have a better estimation of the distribution. Before introducing how minimax estimation changes the way of estimate entropy, let me first introduce an unbiased estimator for best polynomial approximation of function. It's like following. And the polyk in the collection of the polynomials with order at most k on A. And now we can introduce how minimax estimation changes the way we approximate the entropy. First, consider the original way computing the entropies. That is, h of p is equals to the sum of minus pi ln pi. And the mutual information of ixy is just equals to the h of px plus h of py minus the h of pxy. Now we consider the minimax estimation. Before the computing, we assume that the number of samples is n and the empirical distribution is Pn. And then we can compute for each coordinate Pni if the Pni is much larger than the ln n divided by n. Then we use the minus pi ln Pni plus 1 divided by 2n to estimate the minus pi ln pi. And if Pni is much less than the ln n divided by n, there are three steps. First, compute the best polynomial approximation for minus pi ln pi in the region of 0 to ln n divided by n. Second step is that to use the unbiased estimator, which we mentioned in the previous slides, for integer power pik to estimate the corresponding terms in the polynomial approximation for minus pi ln pi. The third step is that use that polynomial as an estimate for the minus pi ln pi. After we change the way we compute the entropy, we can make the comparison between the minimax estimation and the traditional ways. First, we consider the Poisson observation models. And here are the results. We can find that the L2 rate for the minimax estimation is less than the L2 rate of traditional ways. And secondly, we can compare the number of samples that needed to achieve the consistent estimation. And here are the results. We can find that for the minimax of the estimation, we just need the n is greater than the s divided by ln s. But for traditional way, we need to greater than s, which is a huge difference. And then we can apply the minimax estimation to the Chow-Liu algorithms. The first graph on the left shows that the mean square error of the estimation for the mutual information is very large when we use the original Chow-Liu algorithm and is very small when we use the modified Chow-Liu algorithm which applied the minimax estimation. And the result on the right shows that the expected round-edge ratio decreased very earlier than the original Charlie algorithm for modified Charlie algorithm. And we applied the minimax estimation, the number of the samples we need decreased a lot. Thanks for your watching.